All right, so translational momentum, how do we define that in the first place? What does translational momentum mean?
Is it just like the mass and velocity of an object?
Yeah. Mass of the object times velocity of the object. How fast it's moving, including direction, so this is a vector quantity, multiplied by mass. And it's very useful to think of mass here as a difficulty level. The more massive an object is, the more difficult it is to change its velocity. So I find this is a very useful way of thinking about momentum. Momentum is describing the motion of the object multiplied by how difficult it is to change that motion. In fact, if you did want to change the momentum, presumably the mass is not going to change. So if you're writing out delta mv, if the mass is not changing, then you can factor out mass. You can pull a constant out of the delta and just get m times delta v. There are some circumstances where you might want to treat the mass as changing. For instance, if you've got a rocket that's burning fuel, so it's the mass of the rocket with the remaining fuel is getting smaller. Or if you have, like if you've got a conveyor belt that's moving at a constant velocity, but you're putting more boxes onto it, then the momentum of the conveyor belt, including the new boxes, is larger than it was before, even though it's at the same speed. But usually if we're talking about just one object, its mass is staying constant, but its velocity might be changing. And what do you have to do to the object to make it change? What would you have to apply to the object to make that change happen?
A force.
Yeah, you've got to apply a force. And this is where the idea of impulse comes in. Impulse is force applied for some amount of time. And that force times time causes a change in momentum. Add up all the impulses, all of the force times time acting on the object, and you get the total change in momentum of the object. So if there's no force acting on the object, then its momentum does not change. And therefore its velocity does not change either. Let's take a look at the angular version now. Oh, this also applies both to an individual object and a whole system. If you've got an entire system of objects interacting with each other, but there's no external force from somewhere else, no external impulse, then you get no change in the total momentum of the system. For the rotational version though, angular momentum, what's the rotational version of mass?
I times omega.
Yeah, moment of inertia serves the same role for rotation that mass does for translational motion. Moment of inertia is the rotational difficulty, how difficult it is to change the rotation. And then omega, the angular velocity, is the rotational version of velocity. So this is still talking about how fast it's going, multiplied by how difficult it is to change that. So these are the same structure. How fast it's moving times how difficult it is to change that motion. How fast it's spinning times how difficult it is to change that spin. Same structure, just different meanings of the variables. And note that the omega and the v, the translational velocity and rotational velocity, these are vectors, so direction does matter. A change in angular velocity might mean it's changing how fast it's spinning, or it might mean it's changing the direction it's spinning around, the axis it's spinning around. If you've got just a spinning object and you change what axis it's spinning around, this counts as a change in angular momentum. Even if it's going at the same rotational speed the whole time, if it changes what axis it's rotating around, that counts as a change to angular momentum. And if we take a look at that change in L, change in angular momentum is change in I times omega. But here's where things get really different from translational momentum. Translational momentum, we're generally assuming mass does not change. The mass of an object stays the same as long as it's not like breaking up or joining more objects or something. So mass is constant. A change in momentum means a change in velocity. It's just got this extra constant multiplier. For a change in angular momentum, though, angular speed could be changing. It could be changing how fast it's spinning, or it might even be changing the direction of the axis. But also, moment of inertia itself can be changing. Because how are we defining moment of inertia? What is moment of inertia describing? It's describing not only the amount of mass, but also what else?
Where it's distributed. Oh, sorry.
Sorry, what was that?
I was gonna say like where it's distributed based on the pivot point.
Exactly, where the mass is distributed, how far it is from the pivot point. So the moment of inertia is not only about the mass, but also where the mass is, how the mass is distributed around the pivot point. Mass and distribution. The simplest formula for that would just be mass times radius squared. If all the mass is just at the same distance from the center, such as in a ring. For more complicated shapes, if the mass is more spread out in different regions, then you're going to get some formula based on the shape. Usually some fraction times the mass times the distance squared. Because it's got to have units of kilograms times meters squared. So it's typically going to be some fraction times the mass times the distance squared, with the fraction depending on what the shape is, how the mass is distributed. But this still just represents a level of difficulty. Large moment of inertia means it's difficult to change the angular velocity. A small moment of inertia means it's easy to change the angular velocity. And the thing is, though, this can change, because even though the mass is not changing, we're assuming the object maintains a constant amount of mass, the radius could change. You could change the distribution of the mass. For instance, if you're like spinning around with your arms outstretched and you pull your arms in tight, you still have the same mass, but you've made the radius of some of that mass smaller. You've pulled the mass of your arm in closer to the axis you're rotating around. So by making the radius smaller for at least some of the mass, you have decreased your own total moment of inertia. So we can't just pull I out of the delta as a constant always, because I isn't always a constant. Sometimes I can be changing as the object rotates if it's changing its shape as it does so. If I is constant, if you've got a rigid object that's not changing its shape at all, then you can pull I out of the delta. So delta L does equal I times delta omega for a rigid object. If the object is not changing its shape or size at all, if there's no motion of these stuff inside the object, then you can treat I as a constant and pull it out. But if you've got any change in shape, any motion of parts of the object inwards or outwards from the center, I can be changing. So you have to write delta L as delta I omega, like I final omega final minus I initial omega initial. Whereas if it is constant, if moment of inertia is not changing, you can factor that out of the delta like so. But this is one of the big differences between the translational momentum versus rotational momentum. In fact, if we're taking a look at an isolated object, let's assume there's no external forces or torques at all. If you've got one object in isolation, you know the initial momentum equals the final momentum. So M initial times V initial equals M final times V final. Maybe you just got this object drifting through space with no forces acting on it. But if it's just drifting through space with no forces acting on it, what do you know about the mass of the object at some time and the mass of the object at some later time?
It's the same.
It's the same. So we don't even need the initial and final labels. We just got the mass of the object times its initial velocity equals the mass of the object times the final velocity. If it's just drifting through space, there's no forces acting on it, so the initial and final momentums have to be the same. But if it's the same mass also, we could divide both sides by mass and say, in the absence of any forces at all, initial velocity equals final velocity. The object does not change its translational velocity, if there's no external forces acting on it. If we try the same thing for angular motion, though, if we got a rotating object, so if we got rotating in isolation, no torque, because that's what you have to do to change the moment of inertia, change the angular momentum. If you want to look at the rotational version of impulse, instead of force, we'd have torque, because torque is the rotational version of force. So torque times time is our rotational impulse. If you add together all of the bits of torque times time, you get the change in angular momentum. So this is the rotational version of impulse. You apply a force for some amount of time, you're changing the translational momentum of the object. You apply a torque for some amount of time, you're changing the angular momentum of the object. Again, same structure of the equation, just a different meaning of the variables. So if there's no torque, then we can assume that the angular momentum of the object does not change. Angular momentum initial equals angular momentum of final. But if we fill in I times omega for each one of those, initial angular momentum times initial angular velocity, mass and how it's distributed times how much it's spinning at the beginning, has to equal moment of inertia final times final angular velocity. Can we cancel out the moments of inertia like we did with the masses here?
Yes.
Because moment of inertia is always the same before and after?
Yeah.
It's not just mass though, because moment of inertia depends on both the mass and also what else?
The way it's distributed.
Right, and that actually can change. If you've got a rigid object, if the object is not changing its shape or size, if everything's just staying the same distance from the center, then these initial and final angular moment of inertia would be the same and we could cancel those out. But the radius could actually be changing. The classic example is if you've got an ice skater who jumps into a spin with arms outstretched, or if you just like jump into a spin like this, but then you pull in your arms while you're spinning, what happens to your moment of inertia?
Then it changes.
Right. The moment of inertia can change if the object is changing shape or size. It doesn't even have to change its mass. It keeps keeping the mass the same because we do have conservation of mass, but there's no rule saying it can't change how that mass is distributed. So if the object has some way of pulling its mass in towards the center or pushing its mass further out from the center, moment of inertia can change as time passes. And if the moment of inertia changes, what else has to happen?
The angular velocity or omega has to change.
Yeah, the angular velocity is going to change as well. It's not going to change the direction of spin. It's not going to change the axis it's spinning around because moment of inertia is a scalar. A scalar multiplier does not change the direction at all. So the final angular velocity, it still has to be spinning around the same axis that it was before. But it might end up spinning faster than it was before or slower than it was before if the value of I has changed. For example, if you pull your arms in while you're spinning, you're moving your arms closer to the center of mass, closer to the center of rotation. So how is I going to change? Is that going to be an increase or a decrease?
A decrease.
If you're pulling it in closer, radius is decreasing, right? You're making the radius smaller. So yeah, I is going to be decreasing. So if your final moment of inertia is smaller than the initial moment of inertia, if we're changing from, let's say you've got your arms outstretched, so I initial is large, and then you pull your arms closer in, so I final is going to be smaller. What else has to happen to balance that out?
Angular velocity has to increase.
Yeah, you're going to be going from a slow angular velocity to a fast angular velocity. So you can actually change the speed at which you're rotating by changing how your mass is distributed. You go into a spin jump with your arms outstretched, pull your arms closer in, you're suddenly going to start spinning faster. And then if you stretch your arms back out again, you slow your spin back down. So this is basically the only way you can change how fast you're spinning while you're in mid-leap. If you have any torques you have access to, if you can apply a torque to something or have something else apply a torque to you, then you can change your total angular momentum there. But if you're in isolation, if you're just in free fall, if you have no torque acting on you whatsoever, you can still change how fast you're spinning by modifying your moment of inertia. So this is pretty much the foundation of any sort of fancy spin moves in gymnastics, in diving, in space travel. If you want to change how fast you're spinning while you're in mid-leap, while you're in free fall, while there's no other torques acting on you, you can still do this by changing your moment of inertia, changing how your mass is distributed. Any questions on that so far? This also means that if we've got not just one object, but several objects in isolation, if you've got several objects interacting with each other, but with no external torques acting on them, we can use conservation of rotational momentum in the same way we've been using conservation of translational momentum as well. That the total translational momentum can only change if there's an external force acting on the system from somewhere else. The total angular momentum can only change if there's an external torque acting on the system from somewhere else. In the absence of any external torques, we can assume rotational momentum is conserved. So let's try and applying this to one of those examples. Let's say we're looking at let's try this one with the astronaut leaping off of the beam. The idea here is we have this beam and we know what do we know about it? I think we know the mass and the length. I'm going to call that capital M for mass of the beam. And the length is 10 meters. And we've also got an astronaut clinging to one end of it, whose mass is 100 kilograms. And so this is the initial situation. The final situation is if the astronaut launches herself off of the beam. And the astronaut is now moving at a speed of 3 meters per second. So V final for the astronaut is 3 meters per second in a direction 30 degrees above horizontal. And we want to know what's V final for the beam And also, what's omega final for the beam? Because if you launch yourself off of this end of the beam, when you kick off, you're pushing the beam in the other direction. So the beam is going to start to drift the other direction, and also it's going to start to rotate. So we want to know what's the final angular velocity and translational velocity of the beam as you kick off of it, or after you kick off of it. Any questions on that so far? So for the translational momentum, we can assume conservation of momentum here, or translational momentum, because there's no external force. If there was an external force, then the total external force acting on the system multiplied by time, sum of all those external impulses, force times time, tells you the change in total momentum. But we're assuming these are in isolation. There's not even any gravity involved. We're assuming these are far away from any planet. So the total of external forces times time is 0, because there is no external force. So we're assuming translational momentum is conserved here. We can also even apply the same approach to rotational momentum. The change in rotational momentum would be the sum of all of the external angular impulses. External torque times time equals the change to total angular momentum. But again, there's no forces acting on this, and therefore there are no torques either, no external torques. The astronaut and the beam are exerting torques on each other as they push off, but there's no external torques from anything else, and therefore there's no change to the total angular momentum. So we can assume that both of these are conserved independently. We don't mix these together, by the way. Translational momentum and rotational momentum are different quantities. They're not even measured in the same units of measurement. So you can't really add a translational momentum plus a rotational momentum. But you can say that each quantity independently is conserved. Any questions on that so far? So let's try setting this up. Do you want to go through the momentum chart or skip to an equation? Momentum chart can be useful for organizing the information, but the equation might be faster. What do you think?
I think I'm okay with just going straight to the equation, but if anyone else wants a momentum chart, that's fine.
Okay. Any other thoughts? All right, let's try doing the equation then. The chart can be very useful for organizing the information and also for finding certain other quantities, such as the individual changes of each one. But if all we care about is what's the final velocity, sometimes it's more useful to just jump straight to the equation. And that equation in particular is that the initial total momentum equals the final total momentum. And of course, we'll want to split that up into each individual object added together. So the total is going to be momentum of the beam plus momentum of the astronaut. I'll just call those A and B. Momentum of the astronaut initial and momentum of the beam initial equals momentum of the astronaut final plus momentum of the beam final. What do we know about their initial momentum?
It's 0.
Right. If they're not moving yet, then their initial momentum is 0. As for the final momentum, we could write this as, I'm going to work this out algebraically first, just with variables, and then we can fill in values afterwards. If we just write each of these momentums as mv, we've got mass of the astronaut, which we can write as little m, times v final of the astronaut. Plus mass of the beam, which I'm writing as capital M, times v final of the beam. We know both of the masses. We know the final velocity of the astronaut. We just want to find the final velocity of the beam. So how would we do that? How can we solve algebraically for v final of the beam? Without even any numbers, how would we just algebraically isolate this variable?
You would do negative the momentum of the astronaut divided by the mass of the, or the final mass of the beam.
Yeah, because we can just subtract this term from both sides. 0 minus MVA final is just negative MVA final. Then divide both sides by mass of the beam. And we get VB final is negative ratio of the masses times VA final. So it looks like in this case, we might not even need to split these into components. It might be a good idea in other cases, like if you're, especially if you're adding momentums together, you want to split it into components to make it easier to add. But in this case, we can say VB final is just negative little m over big M. That's 100 kilograms over 1,000 kilograms. Times VA final. 100 over 1,000 reduces to just 1/10. So this tells us the final velocity of the beam is negative 1/10 of the final velocity of the astronaut. What would the, ignoring the negative for now, what would the 1/10 multiplier do to this vector? You just multiply a vector by 1/10, what happens to it?
It'll get smaller.
Yeah, you're making it smaller, you're making it exactly 1/10 as large. But what happens to the direction? If you just take some vector and you multiply by a scalar, 1/10, you get 1/10 of the size, and what happens to the direction?
If there's no negative, it'll be the same direction.
Yeah, if we ignore the negative, 1/10 of VA final is just 1/10 that much, but in the same direction. With the negative though, what happens?
The direction is the opposite.
Right, we're gonna get the exact opposite direction. So final translational velocity of the beam is just gonna be 1/10 of 3, so 0.3 meters per second in the exact opposite direction. So we can conclude that V final of the beam is going to be 0.3 meters per second. At an angle of, you could write that as 30 degrees below the negative x-axis. Or you could measure it in standard position. From the positive x-axis, this angle would just be 30 plus an extra 180, so that'd be 210 degrees. So you could describe that as 0.3 meters per second at an angle of 210 degrees from standard position, or you could just describe it as 0.3 meters per second at an angle of 30 degrees below the negative x-axis. Or maybe you might describe that as 30 degrees south of west. 30 degrees south of west, in the sense that if you start off facing west, but then you go 30 degrees south from there, that's the direction we're talking about. So that would be the final translational velocity of the beam. And you could, of course, also do this in terms of components. You could write out the V final of the astronaut in terms of components using sine and cosine of 30 degrees, or cosine and sine, I should say. And then each one of those components gets multiplied by negative 1/10. And then use Pythagorean theorem to find the final magnitude and inverse tangent to find the direction. But algebraically, we can see here that the final velocity of the beam is literally just negative 1/10 times the final velocity of the astronaut. So since that's just a scalar multiplier, we don't even need to do any vector addition here. So there's really no need to split it into components in this context. If all you're doing is multiplying a vector by a scalar, you're going to get a new vector that's parallel to the original, in this case, opposite direction because of the negative sign, but still parallel. And then the scalar modifies the magnitude as well. Any questions on the translational momentum so far? All right, then let's take a look at the rotational momentum. We can still use the same approach. And again, this could be done either using a momentum chart or just an equation. In this case, since we're just going from 0 to not 0, I think the equation is probably going to be more straightforward here. So if we start writing out the equation here, we know that the initial total angular momentum equals the final total angular momentum, because there's no external torque. This is a closed system. There's no torque from outside. The two objects, the beam and the astronaut, are exerting torques on each other, but there's no external torque. So we can assume that the total angular momentum does not change, which means that the initial total angular momentum, or sorry, the initial angular momentum for the astronaut plus the initial angular momentum for the beam equals the final angular momentum for the astronaut plus the final angular momentum for the beam. Initially, it's at rest, though. So what do we know about these initial values?
They're 0.
Yeah, these are both the 0 vector, because there is no rotation at the beginning. Nothing's moving at all. For these ones, though, we're going to write each one of these, as since there is motion at the end, we're going to write each one of these as I times omega. Moment of inertia of the astronaut times omega final of the astronaut, plus moment of inertia for the beam times omega final for the beam. That is final rotational velocity. And again, we can solve for omega final of the beam in the same way. We subtract this term from both sides, we divide both sides by IB, and we get final angular velocity of the beam equals negative ratio of moment of inertia, IA over IB, times omega astronaut final. In other words, in the final situation, the beam is going to be rotating in the opposite direction from the astronaut's rotation, and with an angular speed equal to this ratio times the angular velocity of the astronaut. Any questions on that so far? So we could calculate each of those moment of inertias. I think it tells us the moment of inertia of the beam here, or at least a formula for it. In general, for a beam, specifically a beam rotating around its own center. Because if you've just got an object in isolation, you can assume it's going to, if it rotates, it's going to be rotating around its own center. There's no axle or hinge that's attached to. So we're just going to assume this ends up rotating around its own center as it drifts off in space. And generally, the moment of inertia for a beam around its own center is 1/12 times mass times length squared. Like I said earlier, it's usually going to be some fraction times the mass times the distance squared. If you've got a beam rotating around its own center, that fraction ends up being 1/12. And you can figure this out in the first place by setting up an integral. If you imagine splitting this beam up into lots of little tiny pieces, and each one of those pieces is just some tiny mass times the distance squared from mr squared for the moment of inertia formula. You'd be adding up all those little bits of this tiny bit of mass times this distance squared, plus this tiny bit of mass times this distance squared, plus this tiny bit of mass times this distance squared, and so on. And ultimately, if you're splitting this up into small enough pieces, you'd be using an integral. The integral of radius squared times the tiny bit of mass, dm. And actually setting that up can be complicated because you need to find some way of writing dm in terms of r. So you're integrating dr instead of dm. So it involves some unit conversions and stuff like that, essentially setting up the right coordinate system. But that integral for the beam rotating around its own center works out to 1/12 times mass times length squared. And typically you would just look that up on a data table. Instead of working out that integral every time you want to deal with some shape rotating, if it's a standard shape, you can just look up that shape on a data table listing formulas for those shapes. So we've got 112 times mass times length squared. 10 squared would be 100 times 1,000 is 100,000, so 100,000 over 12. 100,000 divided by 12. Those are both multiples of 4, so we get 25,000 over 3, which is what, 8,333 and a third. So that would be the moment of inertia of the beam. 8,333 and a third kilogram meters squared. I'll just round it off to 8,333. So that's moment of inertia of the beam. Does the astronaut have a moment of inertia? Is the astronaut rotating here? Like at the end, as the astronaut drifts off into space, is she rotating?
Yeah, wouldn't it be?
Technically, yes. She doesn't necessarily have to be spinning around her own axis. She might just be drifting off without spinning. But we're measuring everything relative to that same pivot point. This pivot point right here, the center of the beam. If you take a look at where the astronaut is at several different times, let's say the astronaut drifts off along this line. If you take a look at the astronaut at several different instants in time, here, then a little bit later she's here, a little bit later she's here, then here, and so on. As she's moving, if you trace out the line of sight from the pivot point to the astronaut, the angle is changing. Even though she's moving in a straight line, the angle she makes with the pivot point is changing as time passes. So this does technically count as angular speed. The angle is changing as time passes. That's the very definition of omega. So the astronaut does have angular speed. We're going to need to find a way to calculate that geometrically. Also, since the astronaut is small in size compared to the 10 meters of the beam, we can treat the astronaut as a point object. So moment of inertia of the beam is going to be the 8,333. Moment of inertia of the astronaut, we can just take mass times radius squared because we can treat the astronaut as a small point object. What would be the radius for the astronaut though? What are we measuring these distances from?
The pivot point.
Yeah, and even though the astronaut's not rotating, we still want to define the same pivot point for the whole system. So we're going to measure distance from the pivot point, the center of the beam. How far would that be?
$5 meters.
Yeah, so that's R for the astronaut, 5 meters. So if we multiply mass times radius squared, 100 times 5 squared, that'd be 2,500. So 2,500 kilogram meters squared over 8,333 kilogram meters squared, that gives us our ratio that we can multiply by final angular speed of the astronaut to get the final angular speed of the beam. The tricky part now is going to be finding the angular speed of the astronaut because the astronaut's moving in a straight line. We need a way to convert that translational speed, 3 meters per second, into a rotational speed, how fast the angle is changing. And to do this, it's going to be a lot more convenient to split the angular speed into components. Because if we can split that angular motion, 3 meters per second, into a perpendicular component and a parallel component, the perpendicular component is really all that matters. The perpendicular component is going to make it much easier to find how this angle is changing. So we're going to ignore the sideways direction motion and just look at the upwards direction motion. How would we find that vertical component, that perpendicular component, if we know that the actual speed is 3 meters per second? We know the angle, right? The 30 degrees. If this angle is 30 degrees, and we know the velocity is 3 meters per second, how would we find this vertical side, the perpendicular side?
Wouldn't it be like 3 sine 30?
Yeah, that'll work. And sine 30 is exactly 1/2. So this vertical component is going to be 1.5 from 3 sine 30. So we can treat the astronaut, ignoring the sideways motion, we can just treat the astronaut as if she's moving upwards at 1.5 meters per second. Because if this diagonal motion is sideways motion and upwards motion, the sideways motion doesn't change the angle. If you're just moving directly to the side in the direction of the radius, your angle with the pivot point is not changing. But it's the upwards motion, the motion perpendicular to the radius vector, that actually changes the angle. So we can treat the astronaut's velocity as just the perpendicular direction, perpendicular to the beam itself. So ignoring the sideways direction, we're treating the astronaut as just moving 1.5 meters per second in the perpendicular direction. And now we need to convert that translational speed into an angular speed. And for this, we can actually use the definition of angle. Definition of angle. Radian measure of angle is defined as arc length. Like if you're moving in a circular path, distance along that arc, distance along the circle, divided by radius. So if you've got some angle that cuts off a portion of a circle, that arc length divided by the radius of the circle is the angle. When we say that an angle has a radian measure of 1/3, we mean that the arc length it cuts off is 1/3 the radius of the circle. This is really all radian measure means. So if angle is arc length over radius, then if you multiply both sides by radius, you get radius times arc length, or sorry, radius times angle equals length. How do you convert length into velocity? Velocity is just distance over what?
Time.
So if we just divide both sides by time, we can convert this statement about angle and length, the idea that radius of the circle times angle in radians equals the distance along the circle that you travel if you rotate that angle. If we just divide both sides of this by time, angle over time is angular velocity, omega. Distance over time is translational velocity, v. So if you've got an object moving along a circular path, or even just moving in a straight line, as long as it can be treated as tangential to a circle, this is a relationship between the translational velocity along the circle's edge and the angular velocity of how fast the angle is changing. In this case, we know the translational velocity is 1.5 meters per second because we're looking at just the perpendicular component. We know the radius is 5 meters. So omega is just going to be 1.5 meters per second divided by 5 meters. 1.5 divided by 0.5 would just be 0.3. And meters cancel out, so we just get radians per second, since radians is unitless. So that's the final angular speed of the astronaut. Even though the astronaut is not really rotating, the astronaut's moving in a straight line, but we can treat that as having an effective angular speed of 0.3 radians per second. Multiply that angular speed of the astronaut by this ratio of moment of inertia of the astronaut divided by moment of inertia of the beam, and that'll tell you the final angular speed of the beam itself. And then the negative sign just means rotating in the opposite direction. So the astronaut can be treated as by the right-hand rule, an outwards rotation. That means the beam is going to be rotating in the inwards direction. In other words, spinning like this. But this calculation, 2500 over 8333 times 0.3 radians per second, should tell you how fast the beam is spinning at the end. Any questions on that?
To use the formula r times omega equals velocity, does that mean that the velocity has to be perpendicular to r?
Yeah, this should specifically be treated as the perpendicular component of the velocity. So you would want to, if the velocity is already perpendicular, that's fine. If the velocity is parallel, you would treat it as 0 because it has no perpendicular component. But if the velocity is on some diagonal, you want to split it up. Not necessarily into conventional x and y components, but you want to split it up into a component parallel to the radius and a component perpendicular to the radius. And the perpendicular component is all that matters.
Okay, thank you.
All right, see you next time.
Thank you.
You're welcome.